this is the outline of chapter 27. So we would introduce the single loop circuit, multi-loop circuits, and introduce the ammeter, voltmeter, and also RC circuit. Okay, so this is a single loop circuit. So it's just a single loop. We have a battery here, we have a resistor. So there will be current. Okay, as much as this is positive side, this is negative side. So usually for circuit symbol, I'll write it like this. I'll draw it like this. Okay, I and then R. Maybe we can just put one point to be a ground. Or sometimes I will just make this one like a source. Or maybe a source. This is also a source. Like this. Ow. So as small as this one. So this is E. This is E or Vs or whatever. And then this is I. So this also specify, this is positive side, this is negative side, this is positive side, this is negative side, this is positive side, this is negative side. Okay, so this is a circuit symbol. Okay, so it tells you that we can have an ideal EMF device, real EMF device. Ideal EMF device means, suppose this is a battery. This is a battery, or like this, or like this. Okay, ideal EMF means it will generate a potential difference. Let's say this is E. So for example, if this is ground, this is 0 volt, so this is E. No matter how large this current is, if you connect a larger resistor, the current will be smaller. If the resistor is smaller, I mean the resistance is smaller, then the current will be larger. So yeah, so it only relates to E equals IR. Okay, so no matter how large this current is, the voltage won't change, or the EMF won't change. It is called the ideal EMF. Ideal EMF. So if you draw it like on the x-axis is I, and y-axis is V. So V is also it's always a constant. So this is E, no matter how large this current is, even if it is positive, negative, or 0. Okay, the slope is 0. But here, for a real EMF device, it's just like a battery. So if it is a real EMF, it should be like an ideal E connected series with a resistor. Although the resistance might be small, but it will influence the generate voltage. But because this is for example, this is A, this is B. Okay, this is A, this is B. Okay, so when you see the voltage V here, then you can see IV. It will be something like this with a negative slope. The slope will be like negative R. Okay, so if there is no current, this is E. This is also E because there is no current going through this resistance, so there is no voltage drop. But if there is a current, a larger current will make here a larger voltage drop. So for example, this is E. This will be smaller. Okay, it depends on how large this loading is. If there is absolutely low current, then there will be no voltage drop. But if there is a large current, if R is also small, then the current is large. Current is large, this point the current is large, there will be large current going through this R. So there will be a large voltage drop here. So it turns out to be like this. So this is ideal and real RMF device. Okay, so here you talk about the single loop circuit. Single loop circuit is easy. This is E. this is out. So maybe we can just write it as this is E, this is out, like this. Or maybe we can just put a single point to be a ground. So make it a ground. Okay, so this is I. So this is nothing but I equals E over R. E and R are unknown variable, so I will be E over R. So nothing special. Okay, yeah. Okay, so here we will use, actually, for this simple circuit, we don't necessarily need this so-called KVL, Kirchhoff voltage law. Kirchhoff voltage law. Okay, before we have talked about the Kirchhoff current law, which means that for a single node, the total current going in and total current out are the same. Here, we talk about the Kirchhoff voltage law, which means that, for example, here, we start from here. This is the ground of the circuit. So let's say we go in this way. So we go across this EMF, which means that this is 0 volt. This is E. So here it will be E. And then after going further and then going back. Okay, this is a resistor. We will have a voltage drop. Okay, so after we going back to the original point, this should be 0, because in chapter 24 we have the equation like in integral of E dot ds should be 0 if there is no magnetic flux, magnetic field changing. Okay, we have this one. So we have going for the whole loop turns out to be 0. Okay, so which means that this is for the textbook it write it as VA, or maybe VA. You can just consider it's VA adding E, because this is negative, this is plus. So we add E, and then here we have a voltage drop IR. So we minus IR, going back to the original point VA. So the final step is a cancel VA. So you can just put VA to be 0. So for simplicity. So finally we get E equals IR using the KVL. Although it is too simple to use the KVL, but yeah, just let you to familiar with the KVL, so we can use it later on. So here we have a loop rule. In the textbook we call it loop rule, but usually I call it KVL. I usually call it KVL. And here the resistance rule is nothing but the Ohm's law. I don't know why it introduced too much terms here. So the EMF rule is nothing but the voltage source. The voltage source, or the battery, or you can consider it's a battery or a voltage source, or a battery. Okay, so here is a slightly more complicated case. So we have a real EMF. So it has an ideal EMF E called series with a small resistance, small R, and then later on we connected with a resistor R, capital R, and then going back here. So here we have the ground. Okay, VA, you can make it 0. Okay, so we go in this direction, going here, go through this battery, negative side, positive side. So we add E. Okay, so here we just add E, and then after going through this part, okay, so you just try to cut it out, and then you try to expand it. So this is A, and then the EMF, and then the battery, and then point B, and then also the resistor R, and then going back to point A. Okay, so just try to cut it and then expand it like this. So here, from 0, VA to going up by E, and then going across this small resistor, so there will be a voltage drop IR. And then this is node B, so the voltage doesn't change. and then this is I out. So we drop for I out, going back to the original point. So the potential should be the same. Okay, so which means that we should have 0. Okay, original point is 0 plus E minus I out minus I capital out equals 0, going back to the original point. This is the original point, ideal EMF, and then small resistance, big resistance, going back to original point. So we can just move this part to the right side, and then finally we can get I equals E over capital Alpha out. So nothing special. You can just consider it as this is E, and then this is out, and then this is also capital out. So this is like a series resistor. Series resistor is like the summation of them. So it turns out to be E. This is E, and then this is R plus capital R, like this. E, R plus capital R. So we have E over R plus capital R, as simple as this one. Okay, so here we also here we talk about the series resistance. So yeah, so actually it is just like if we have E, R1, R2, R3, so we have a original point go up by E, so we have plus E, and then minus IR1, minus IR1, minus IR2, minus IR3, going back to the original point equals 0. Okay, so we move this three terms to the right side, and then divide R1 plus R2 plus R3 on both sides. So we have I equals E over R1 plus R2 plus R3. Okay, comparing with this one is REQ, the equivalent resistance. Okay, if both are the same thing, we have I equals E over REQ. So REQ should be the same as R1 plus R2 plus R3. So REQ. So this is the series resistance. We just add them together. Okay. Series resistance. We just add them together. And then the next case is we don't talk about the parallel resistance immediately, so it doesn't really matter. So here the potential difference means you can just pick 2 points. For example, if you just pick B and A, you can also calculate the potential, electric potential between node B and node A. Okay. For example, here we just consider the potential difference VB minus VA is like VBA. So VBA or equals VB minus VA will be this one going from here. Here is VA equal starting from this point is VA, and then going through this EMF plus E, and then going through this resistance minus IR equals, this is VB. Okay, so we just move this one to the right side. VB minus VA is this one, E minus IR. And here it also mentioned that you can grounding a circuit. So which means that for a whole circuit, you can just pick any of the point to be with a 0 volt. Grounding a circuit usually means to connect one point in the circuit, only one point. Don't try to connect for multiple points. Connect one point to the circuit, to the conducting path, to the earth surface, actually to the electrical conducting blah blah blah. So it will sometimes simplify the circuit. Okay, power of the EMF device. Okay, so for the power of the EMF, we have I times E. So before we know for the power consumption should be P equals IV. Okay, so VE is actually similar thing to the voltage. So here I times E or I times V for I times V is actually suitable for any device, even for nonlinear device. It is also correct. So you can just try to remember this P equals IV. Okay, so let's try to